In this video, we're going to talk about vector notations and magnitude and direction of a vector. So I want to begin by defining what a unit vector is. So a unit vector is a vector of length 1. So we technically haven't talked about how we determine the length of a vector yet. I will talk about that later in this video, but it's helpful to have this idea of a unit vector to introduce some notation on vectors that'll make the theory of magnitude and direction a little bit easier to state afterwards. Okay, so I want to begin by stating what the standard unit vectors are. So the standard unit vectors, I'm going to introduce some notation. So I'll write an I with a hat on top of it. I'll write a J with a hat on top of it, and a K with a hat on top of it. Okay, so these are all vectors of length 1. I hat it's in the direction of the positive x-axis. So it's in the positive x direction. J hat is in the positive y direction. And K hat is in the positive z direction. So I'll draw a picture to illustrate what these look like. But one thing I want to note about these is, notice that all of these, the I hat, J hat, K hat, they're vectors, because we're also talking about the direction that they're pointing in, but I'm not using my arrow notation. I'm using this hat symbol. So the convention is that we use this hat symbol instead of the arrow for unit vectors. So when we see a letter like this, notated with a hat on top of it, that means that it's a unit vector. Okay, so let's draw a picture to show what these look like, the I hat, J hat, and K hat. Okay, so I'm going to draw my x, y, z axes, so that'll be my z-axis. This is x. Okay, and then I'll have y-axis extending this way, and then I'll draw the negative directions. So negative z goes down, negative x goes this way, negative y extends that way. Okay, so I hat is a vector of length 1 that points in the positive x direction. So I'm going to draw it emanating from the origin. So emanating from the origin, but it'll point in the positive x direction, so that's this way, but it'll have a length of 1. So that means it reaches to where 1 is on the x-axis. So that is the vector I hat. All right, so now let's draw J hat. So J hat also, I'm going to draw it emanating from the origin. It'll point in the positive y direction, so that would be this way. It'll go a length of 1, and that is J hat. And then finally K hat, I'm going to also draw it emanating from the origin, and draw it straight up in the positive z direction. So positive z direction, that would be straight up. It has a length of 1, and that is K hat. Okay. So the nice thing about having this notation for these standard unit vectors, these vectors of length 1 in the x, the y, and the z direction is, I can write any other vector that exists in 3D space in terms of these 3 standard unit vectors. So let's do an example. So in this example, let's draw the following vectors. So in part A, I want to draw 2i hat minus 4j hat in the xy plane. So that means this is a 2-dimensional picture in part A. Part B, I have 2i minus 4j plus 3k in xyz space. So sometimes, just to save a little bit of time, when I say these out loud, I might not always say I hat, j hat. Sometimes I might just say I, j, k to refer to them. Okay, so let's talk about each of these. So let's begin, let's keep this in black actually. So part A, my drawing is going to be in the xy plane. Okay, so I'll have my x axis, and then we'll have the y axis. And let's put some tick marks. So I'll go 1, 2, 3, 4, negative direction, negative 1, 2, 3, 4, y direction, 1, 2, 3, 4, negative direction, 1, 2, 3, 4. Okay, so for my first vector, 2i hat, that is going to be in the same direction that I hat would be. So 1 in the positive x direction, But multiplying by 2 means it's twice as long. So 2I hat looks like this. That is 2I hat. It extends and has a length of 2. What about minus 4j hat? So multiplying j hat by a negative number means that now it's going to be pointing in the negative y direction, and the 4 means it's going to have a length of 4. So negative 4j hat extends all the way down to negative 4 on the y-axis. So this is what negative 4j hat looks like. And we need to add these together. So I'm going to do our parallelogram law. So I'm going to make a parallelogram. In this case, that's actually just going to be a square. Okay, so now I need to draw the diagonal of this. So starting at the tips here, and sorry, not the tips, this would be the tails of these vectors. And I draw a vector to the opposite corner of this parallelogram. And that is 2I minus 4j. It's 2I added to negative 4j. All right, so there is another common way that a vector like this is notated, and that's what's called a component form. So component form. So notice that this vector basically depends on, it's basically drawn to the point 2 comma negative 4. And there's another way that we can notate that. We express it in these sharp brackets, and I put 2 in the first spot, and then I put a comma, and then I put negative 4. So basically what I do is I sort of put the x component, or sometimes it's called the I component, first, and then I put the y component second, or sometimes that's called the j component. Okay, so I'll say that this is the I component, and the negative 4, that is the j component. Okay, but these mean the same thing. 2I minus 4j, or in the brackets 2 comma negative 4, they both refer to this vector. All right, now let's do part B. Let's keep this in black though. So part B. So I need to draw my x, y, z axes this time. So let's have z going straight up, x coming out to the left like this, coming out of the board, y going straight to the right. And now let's draw their negative directions. So negative z extends straight down, negative x would extend this way, and then negative y would extend to the left. Okay, so now, so I need to draw where the point 2, I need to draw where the point 2, negative 4, 3 is. So to do that, we need to go 2 in the x direction. So 2 in the x direction would be, let's say, somewhere here. And then I'm going to have to go negative 4 in the y direction. So let's say that's here. And now, just like we've done before when we've drawn points, I'm going to draw a line through 2 that's parallel to the y-axis. And then starting where negative 4 is on the y-axis, I'll draw a line parallel to the x-axis. And then I have this point right here. Okay, and now let's draw where 3 is on the z-axis. So let's say 3 is somewhere here. And I'm going to make my rectangular solid. So let me start where 3 is on the z-axis, draw a horizontal line parallel to the y-axis, and then draw straight down until I reach that negative 4. And that's sort of the back wall of my rectangular solid. And then I'll draw up from this point a vertical distance of 3, and then I'll draw a slanted line parallel to the x-axis. And then from this corner, I'll draw a horizontal line parallel to the y-axis until I get above the 2. That's another corner. And then draw straight down until I get to the 2. And now our rectangular solid is almost done. From this corner, I just connect it with 3 on the z-axis, and I got my rectangular solid. So the vector that we want to draw here would start at the origin and would go to this point, to negative 4, 3. And that is the vector that we wanted. It's 2I minus 4j plus 3k. So the fact that this is a vector, it has this length, that it has this direction, makes it a vector. So it's not just the point, it is a vector. Okay, so in component form, I would have my hard brackets, but this time there are going to be 3 components. The I component would be 2, the j component is negative 4, and the k component is 3. All right, so now we've drawn these vectors, and we see what this ijk notation looks like visually, and also how we translate this to this component form notation. So next, let's define the magnitude of a vector. Okay, sorry. So we kind of jumped down a little bit, but this is where I actually want to be. So the magnitude, which we also refer to as the length or the norm of a vector, so of the vector v, which is ai hat plus bj hat plus ck hat, where the a, the b, the c are, so this symbol, this first symbol, means that they are elements of, and that second symbol that looks like a capital R with an extra vertical line means the reals. So a, b, and c are reals. They are real numbers. In other words, they are scalars, whereas the I, the j, and the k are vectors. So this is notated by writing the vector with two vertical lines outside it. That's how we sort of notate the magnitude or the length. And the formula for the length is it's the square root of a squared plus b squared plus c squared. And where this actually comes from is the distance formula, which involves using the Pythagorean theorem. So one thing that I want to comment on about this notation is the book uses a different notation to represent the length. Just slightly different. It writes the vector, but just inside of one pair of bars. So kind of like an absolute value. But the majority of people typically write these double bars. So that's how I'm going to be notating the length of a vector. All right, so let's do an example. So what's the magnitude of the vector from the point P1, which is negative 2, 0, 7, to the point P2, which is 1, negative 4, 2. So what I need to do first is I need to find the vector that begins at P1 and it ends at P2. So I'm going to notate that like this. So I put an arrow on top of it, which means it's a vector. And the fact that I wrote P1 first means it starts at P1. And P2 second means it ends at P2. So first up, I need to find that vector. So to find the vector that connects these 2 points, starting at P1, ending at P2, would be, I'm going to use my component notation. And what I'll do is I'll subtract their sort of x components or their I components. But I have to do P2s minus P1s. So I have to do 1 minus negative 2. The order matters because I have to begin at P1 and end at P2. So for their j component, again, I'll do negative 4 minus 0. The order matters. For the k component, I do 2 minus 7. All right, and then simplifying this, we get in brackets 3, comma, negative 4, comma, negative 5. All right, so at this point, we are ready to evaluate the length. Because I have the vector, now I'm ready to get the length. The length is going to be, using our notation, I write the vector P1 and P2 in these double bars. And the formula says, well, I'll take a square root of the I component squared plus the j component squared plus the k component squared. Okay, so this will be 9 plus 16 first, that's 25, plus another 25, which is 50. 50 square rooted. And I could pull a 25 out of the square root and have it become a 5, and then be left with a root 2. And that's our length. So in general, I can write down a formula for the vector from a point P1, which I'll write as x1, comma y1, comma z1, to another point P2, which I'll write as x2, comma y2, comma z2. In general, that formula would be P1, P2, let's put a vector arrow on top of it, is in component form. So it's the second x coordinate minus the first x coordinate, comma, the second y coordinate minus the first y coordinate, comma, the second z coordinate minus the first z coordinate. Okay, so that is a formula for the vector starting at P1, ending at P2 in general. All right. Okay, so I'm going to go back and I'm just going to highlight this formula I had for the magnitude because this one is definitely important. I'm going to go ahead and highlight this formula for the vector that connects P1 and P2 that has its tail at P1 and its head at P2. Okay, so the next thing I want to define is the direction of a vector. Okay, so the direction of a vector v is defined to be the unit vector pointing in the same direction as v. Okay, so the key question now is, so if I want to write down the direction of a vector, I need to find the unit vector that's pointing in the same direction. So how do I get that unit vector? And that's what the following theorem will tell me. So there's a blank in this theorem that I'm deliberately going to fill in. So the theorem says, if my vector is not the zero vector, and I want to get a unit vector that is pointing in the same direction as v, what that vector will be is, it'll be v divided by the length of v. And we'll do an example of this. So for right now, I just want to highlight this formula. And now let's look at an example. So here's the example. Let's let v be the vector. And actually, I'm going to change one of these signs. I realize it's kind of want to use the same vector that I had in the last example. There, it was a -5 as opposed to a positive, so I'm going to change that sign. So let's let v be this vector, 3i minus 4j minus 5k hat. Oh, oops, and I forgot to put hats on a couple of these. Okay, so let's fix that. We already know what the length of that vector is, because we found that in the previous example. It's 5 root 2. Well, let's find the direction of v now. Okay, so let's talk about the solution. What we need to do is we need to get a unit vector. I'm just going to abbreviate vector, VEC, in the same direction. I'm going to abbreviate direction, DIR, as v. So to do that, we use the formula that I just stated in the theorem. We take the vector v and we divide it by its length, by its magnitude. Okay, so we can write this as 1 over the magnitude. That's just going to be some number. And then multiplied by the vector v. Okay, so this right here is a vector. It's the vector v. And this fraction in front of it, 1 over the length, is a scalar. So the magnitude of a vector is now just the length. So this denominator is just a length. It's just a number. And 1 over just a number is just a number. So this is going to be a scalar, not a vector. Okay, so we have 1 over the length of v, we know, is 5 root 2. And that needs to be multiplied by the vector v, which is 3i hat minus 4j hat minus 5k hat. Okay. So it turns out that when we have a scalar like 1 over 5 root 2 multiplying a vector like this, it turns out that the scalar, in this case as 1 over 5 root 2, this whole thing, distributes. That's a property that we are going to see in the next video. Okay, but I think it's something that we'd sort of intuitively expect to be true here, so I'm just going to go ahead and use it, although we'll see it again more formally in the next video. So if we distribute that, we end up with 3 over 5 root 2 I hat minus 4 over 5 root 2 j hat. And then the next term would actually be minus 1 over root 2 because of the 5's cancel k hat. Okay, and that actually is a unit vector now, and it's going to be in the same direction as the original vector. I think it's easier to see that this is in the same direction as the original vector because all we've done is we've just taken the original vector, multiplied it by a scalar, and we saw in a previous video that when you take a vector and you multiply it by a scalar, all it does is it either sort of stretches it out, or it shrinks it, or if you multiply by negative, it will put it in the opposite direction. But overall, it sort of preserves that direction. In this case, we're multiplying by a positive number, so it's still going to be in the same direction, not even the opposite direction. The question I want to ask is this really a unit vector? Because I just stated a formula and I kind of asked you to just trust me on it. But let's check, is this actually a unit vector? So let's check. The way I would check if this is a unit vector is, I would find its length and just look to see if the length is 1. So let's take the length. So let's take the first I component. So let's take the I component, square it, and then the j component, square that. So minus 4 over 5 root 2, square that, and then the k component, square that. Sum those all up, and then put that in a square root. That's how we find the length. Okay, so the first fraction is 9 over 50. The next one's 16 over 50. And the next one is 1/2. So all in a square root. So simplifying, again, a little bit too far ahead of myself. Okay, so adding the first two fractions, we will get 25 over 50. And then if I get a common denominator with the 1/2, that is also 25 over 50. So 25 over 50 plus 25 over 50, 50 would be 50 over 50, or 1, which is 1. And that's what we wanted. We've now shown that the length of this vector here is 1. So it is a unit vector. And that's going to be true in general about that formula that we stated, this formula right here, that produces a unit vector in the same direction. All right, so what I want to end this video by doing is by noting something about the length and the direction of a vector. So notice that in the problem that we just did, whoops, I got to fix this sign. This should be a minus. I think it was minus 1 over root 2. Yeah, minus 1 over root 2. So in this problem that we just did, the vector v is 5 root 2 times this unit vector. If you multiply 5 root 2 and you distribute that into each of these terms, you'll end up with the original vector that we had, which was, what was it? It was 3i hat minus 4j hat minus 5k hat. Let me zoom out a little bit, in fact, so we can see that a little bit more. So zoom it out. Okay, and now I want to state something general about this, which is what this formula says is that v equals, so 5 root 2 is its length. So v is equal to its length times this vector here. But what was this vector? This was the direction of v. Remember, the direction of v is the unit vector that's pointing in the same direction that v is pointing in. Okay, so that is true in general. Alright, so in this video now, we have finished our third goal, which is we've introduced some new vector notations, so the ijk notation and the component form notation, and we've defined the magnitude, or in other words, the length of a vector, or the norm of a vector, and the direction of a vector.